Okay, next up we have Hendrik Eeckhaut, there he is, and he's the TLSNotary team lead at Ethereum Foundation, and he'll be giving a talk on verify private web data with TLSNotary. Big round of applause, everyone, for Hendrik.
Good morning. Thank you for the kind introduction. So today I will introduce TLSNotary to all of you and figure out how we can share and verify private data on the web. So short info about me. I'm Hendrik. My Twitter handle is Eeckhaut. I'm the team lead of the TLSNotary team, which is a research team in the Privacy and Scaling Explorations Lab, which is a part of the Ethereum Foundation. So the overview for today, a little bit cryptic, but I start with the why, what exactly TLSNotary is, how it works, and where and who, where you can use it, who can use it, and to make it prove that it actually works, I also have recorded a few demos. So first, why are we building TLSNotary? And it's all about portable data. So Alice has access to some of her data on a website. She logs in, gets her data, and gets it through HTTPS. And the question is, how can Alice share that data with Bob? So what kind of information could it be? This could be like any private information, like identity information from a government, financial information from a bank, private messages, but it could also be gaming assets or whatever. And then why would Alice want to share that with Bob? Maybe Bob needs to do KYC or wants to give a loan to Alice. All these kinds of information where Bob needs to know that the data that Alice shares is true. So Bob needs to be able to verify the authenticity of the data. So HTTPS is built on TLS. So it's a security protocol with encryption. I assume most of you use it every day. But so TLS provides authenticity. So Alice knows that the data comes from the website and not from somebody in the middle. So that's through certificates. It also knows, because of the key exchange, that the data she gets is, has integrity, so nobody changed it along the way. And also, because of the encryption, Alice has privacy. Nobody can eavesdrop between the website and Alice. But unfortunately, what TLS does not provide you is portability. So I'll go into that in more detail later, but so TLS uses symmetric encryption. So once the data is on Alice's computer, Bob does not have guarantees that Alice didn't change anything to it. So in a nutshell, already pitching TLSNotary. So TLSNotary is a protocol that has all the advantages of TLS and also adds portability. So it's a way for Alice to share data with Bob so that Bob can verify the data. So Bob does not need to trust anybody else, but maybe except for the data on the website itself. Also to the website, it's invisible that TLSNotary is going on, and there's also privacy guarantees that I will dive into in the next minutes. But the whole advantage of doing all this is that actually all existing data on the web becomes composable. So without approval from websites, you can kind of assemble and collect data the way you as a user want, and then get services based on that data. And that enables a whole lot of new applications. So let's take a few steps back and talk again about why can't Bob trust the data that Alice has, because it was encrypted at the server side. So the thing is that Alice and the website use the same key. So it's symmetric encryption. So once it gets onto Alice's computer, Alice could like change the data and use the key again to sign it or something. But so that doesn't work. So Bob, if there's any meaning to the data, needs more guarantees and need to be able to verify that the data is correct. So what are some systems to do that? You could like use like public key encryption on the server side. So the website just signs off on the data with asymmetric encryption. That would be a very elegant solution. And then you just use some ZK proofs and everything would be done. But unfortunately, the big disadvantage there is that the website needs to cooperate. And in practice, there is very little incentives for the websites to do the extra work. It also might have more implications. So that's not something that I expect to happen soon. I hope it will in the end. That's actually the end goal of TLSNotary, but there's still a lot of steps to take. Another option that is used very frequently today is OAuth. But again, that requires cooperation of the website, and it also adds more assumptions, like now the OAuth server could censor, the OAuth server knows what you're doing, and some more trust assumptions there. Another option is to involve an intermediary. So Alice could query the data through this intermediary, and then the intermediary could sign off on what it had seen. And then if Bob trusts the intermediary, then he also knows that the data is authentic. So the advantage is nothing needs to change on the web server. But of course, it's one intermediary, so the website could like easily block that intermediary if he doesn't want this to happen. And of course, there's also trust assumptions again for the intermediary. So what we propose is to use multi-party computation. So that Alice and Bob needs to cooperate to get data from the website. And the advantages are clear. So the website doesn't need to cooperate. Privacy is guaranteed because Bob only sees encrypted data. And it's also secure because Alice cannot fetch the data and then share it with Bob if she tried to cheat in the protocol. Of course, it's also not free. So it will add more latency to the connection to the website. And of course, there's, because of MPC in its current state, there's also a lot more bandwidth between Alice and Bob than just the bandwidth for fetching the data. But that's a lot of work in progress, so we're improving that part as we move forward. In the previous slide, I said Bob only sees encrypted information. That wouldn't be useful. So what it actually means that after the TLS session ended, Alice can share unencrypted data with Bob, because there's commitments to the encrypted data. Bob can verify that this happened. And in that process, Alice can redact certain parts of the transcript. So for example, if there is authentication tokens or anything in the headers, or if the Bob, the verifier, only needs to know a username and nothing else, then you can redact everything except for the username. And also, This can be further enhanced with zero-knowledge proofs that instead of just sharing your address, you prove that you're not in the US, or instead of sharing your birthday, you prove that you're 18 plus. So that's at the use case side. So to summarize already what I did in the introduction, so a TLSNotary solves a conceptually simple problem. So how do you query web servers and share the data with another party in a way that's secure, verifiable, and privacy preserving? So let's take an extra step and see how exactly that MPC TLS works. But before we dive into MPC TLS, a short recap on how TLS works first. So there's a key exchange first. So that's with elliptic curve Diffie-Hellman. So Alice shares her public key with the server shares his public key. Then they do this key exchange and both derive a session key. And so the session key is this symmetric key. And once they have this key, then Alice can do a request encrypted with the session key, that the server can decrypt it, encrypt the response, and send it back to Alice. So how does it work in TLS MPC? So note that I will, from now on, I will say prover instead of Alice, and I will say verifier instead of Bob. So here we follow a different scheme where the verifier first shares his key with the prover. The prover shares a combination of the prover key and the verifier key with the server. And then the server just sent his public key back. And then we do an MPC, so a multi-party computation, where the prover and the verifier calculate the session key together. But in the end, instead of the prover or the verifier having this symmetric key, they only have a key share. So they can only encrypt and decrypt messages with the server if they cooperate. Also note, so I've put this MPC box there. So that's not a computer that's there in the middle. It's more kind of a hallucinated computer. So this is actually the prover doing computations on his side, exchanging messages with the verifier, also doing calculations there. So it's actually like oblivious transfer and garbled circuits behind the scenes to do all these calculations. So how does encryption then work with MPC TLS? So it's an MPC where on the prover side, there's the prover's key share and also the plain text of the request. So that's mostly HTTP request. And on the verifier side, it's the verifier's key share as private input. And through this MPC, they come up with the encrypted text, which is the ciphertext. And then something I didn't show in the previous slide, it's you don't simply send the encrypted text, you also add a message authentication code there, which is kind of like a checksum, which is a G-hash here. And then so you also have to calculate that and then have the authenticated ciphertext. The way this works is that the prover cannot communicate with the server without the verifier's cooperation. And because the verifier participates here, in the end, when he gets the data back, he can verify that there was no cheating going on. Decryption is very similar. So prover so the prover receives the ciphertext from the server. That's as input for the MPC. With the key shares, they check the message authentication code. if that is correct, then it's authenticated and they can do the decryption. And in the end, only the prover sees the plain text, but of course the verifier has seen the encrypted text, and because of during the decryption, it also got commitments to all of the bytes that were exchanged. So in a nutshell, so prover and verifier have to work together to do encryption, decryption. The verifier cannot see the plain text, and the prover cannot forge requests nor responses. And also only the prover communicates with the server. So from the server's perspective, this is the same as any other TLS connection. So I've prepared a quick demo for this, where in this scenario, there's a prover which has access to the Star Wars API server, and the verifier wants to get information about Luke Skywalker, and the prover will share that, but it will redact the home world. So let's hope this works. So I have the prover on the left and the verifier on the right. And so I start with running the verifier as a command line server. And on the left, I have the prover in a web browser. And so the first thing that happens, there's a lot of text scrolling by, but that's the multi-party computation setup. So that's exchanging input for the garbled circuits. And then once that setup is complete, they start communicating with the server, exchanging keys, and then also doing the encryption and decryption. And then in the end, the verifier gets the redacted data. If we zoom in here on what the verifier saw, is that we have an encrypted header there, and also in the JSON you see we did redact the home world. So where is this applicable? So anywhere where you need to share private information. So this could be identity, but also financial information like records from your bank, or that you own certain stuff, and also social things. But there's actually a very wide range, and I leave that to your imagination. And I'm also very curious to hear what you come up with. But so in a nutshell, everything, all data becomes composable that way. TLSNotary is already used in a few very nice applications. So for example, ZKP uses TLSNotary to prove transfers on Revolut to do to exchange on-chain tokens. Another example is OpenLayer, where they made this fun application where you can prove your gains or losses on Robinhood. So it's you proven returns on your investments there. Also, Opacity Labs, a sponsor here, made this very funny app where you prove genetic things from 23andMe. So you could have your baldness score or your Neanderthal percentage, but talk to them or go to the workshop later today to learn more about what they're doing. A refinement here. So until now, I've only spoken about 3 parties: a server, a prover, and a verifier. But in a lot of use cases, there's multiple verifiers that want to verify the same data. And just doing this whole dance over and over again might be too expensive. And so in that case, it might be interesting to delegate the MPC TLS verification to a third party. And that's where the notary in TLSNotary comes from. So you have a separate party just doing the MPC TLS, and then the sharing of the data is done with the verifiers. But note that in that case, it's a signed attestation. So it was delegated verifiability here. So verifier and the need to trust that the notary actually did the MPC TLS verification. Because the notary signs off, it attests that it saw that the MPC TLS transaction was authentic, but the notary key could be used to sign whatever. So always be careful if you just get a random proof. In that case, you need to trust the attester. I also recorded a demo of this setup. In this case, the prover will prove that he received a direct message. It will be notarized by a notary server we ran, and then you get a JSON file for the attestation, and then that attestation will be shared with a verifier that will just visualize that DM. So let's see. Oh, you can mute the audio. So in this case, we use the browser extension for TLSNotary. So we install a plugin for getting a Twitter DM. And then when you start this, it opens a side panel. It guides you to the Twitter website. It checks and uses the cookies there to do the requests. And then we see something similar as we saw in the previous demo. So we do the whole MPC dance. And then in the end, we get an attestation, which is for now just a JSON file, but that format will change. And then you see like there's encrypted headers, and then no redactions in the response. And now we will open a demo website. We have explorer.tlsnotary.org that you can also use to visualize data in proofs. So again, if we zoom in, we see the sent data and the received data. And then you can see that the DM is in there. So that was just to show that TLSNotary, it's a Rust library. You can run it natively or through WebAssembly, run it in a browser. We're working on this plugin system because the challenge is always how do you get the cookies or the secrets to do the response to get the private data, and this browser plugins helps you with that. So most users already do log into Twitter servers or whatever the data is. So you can reuse the cookies in that system or to get the secret headers you need to do the requests. And so that's a convenient way to do it. One thing that's a disadvantage of using TLSNotary in a browser is that the browser cannot do a TCP connection. So to work around that, you need a WebSocket proxy, but that's easy. That's also something a user could run locally, or you could use a hosted service for that. But please play around and see what you can come up with. So TLSNotary is an open source project. It's dual licensed, so you can pick either Apache or MIT at your option. So it's written in Rust, and you can also, through a WebAssembly, use it in browser environments. And we have a browser extension that we'll work on that makes it easy to extend TLSNotary to use it for your specific use case. So, getting started, we're very eager to learn about all the ideas you have. We have a quick start that helps you to do some experimentation either in Rust or in the browser. And to summarize, if you want to query web servers and share that data in a verifiable way, where privacy is also important, then use TLSNotary and give us your feedback. So here again, the pointers. So,
We'll take any questions from the audience. Okay, let's go with you there in the gray shirt. No, that one.
I wanted to ask about that hallucinated machine, like you called it. So a party that is going to actually touch the shard of the both prover and verifier and do necessary computations. In the real world, who is that party, and do we need to trust it as a prover or verifier?
Sorry, I missed the first part of your question.
Okay, so I wanted to ask about this party that you called the hallucinated machine in the first part. So the party that is going to touch the key shard of both prover and verifier and then do some computations on it. Who is going to be this party in the real world? And also, do we need to trust that party?
So in the real world, it is the two parties. It's the prover and the verifier. And so the prover only sees his secrets and the verifier only his secrets. And then it's like a cryptographic protocol where they exchange messages. So oblivious transfer is like a way to share information while keeping it secrets. But it's a bit too complicated to...
So there is no third party, actually.
No, that's the hallucinate. It's easier to think of it as this thing computes something, but that thing doesn't exist. It's that's the encryption, the MPC that's doing that.
Okay, thanks.
Yeah.
Okay, and I think we'll take one last question. I think the man there in the hat. Okay. Okay. Okay.
I'll be quick like that. We can have two questions. Can you give more details on the reduction part? Like when you explain that you know about Star Wars, but you don't know about the word and you are just hiding it. Yeah. How do you do this hiding part?
So during the MPC TLS, the prover commits to bytes that he received or decrypted, and then the prover decides which bytes get disclosed to the verifier.
So I want to ask about a way which is probably too complicated for the prover, but I'll ask anyway. In the current TLS, you have a Diffie-Hellman exchange and you have symmetric encryption of the data. And the problem is that the prover cannot prove that this exchange, that the data was encrypted with this key without exposing their private key. Can't they use ZK to prove that the data that they got was encrypted by symmetric key, which came from the Diffie-Hellman exchange?
So it's symmetric encryption. So you could then, I think, just encrypt something else with that same key and have that proof. So it would be not the that wouldn't work. So it's interactive.
Okay, thank you.
Yeah.
Thank you. A big round of applause for Hendrik.
Yeah. And if there's more questions, I'm here all day, so just talk to me and we can discuss.
Amazing, thank you. And now it's time for the networking break till 12 p.m. And afterwards on the main stage at 12 p.m. we have Marek from vLayer Labs, delivering his keynote. And please make sure to check out the agenda. There's also talks happening in the workshop room and the side stage. So make sure you have a look so that you can decide what you want to see next. Thank you.